Hello, welcome you all in organic photochemistry. Today I will explain energy transfer process in photochemistry, energy transfer between the same molecule or energy transfer between the different molecule, that is intermolecular energy transfer or intramolecular energy transfer. In my previous lecture I told you about the Jablonski diagram where I discussed various relaxation processes, how the electron get relaxed back to its lowest ground state. So one of the relaxation process that was intersystem crossing, and this intersystem crossing is a very important relaxation process, and it takes place between the state of different multiplicity. Suppose if electron is present in excited singlet state, then it relaxes to the excited triplet state. Suppose this is S1 and this is T1. So these two states is having the different spin multiplicity. This is having spin multiplicity of 1, total spin multiplicity, that is 2s plus 1. So here this 2s plus 1, this is equal to 1 here, and this is equal to 3. So both is having the different spin multiplicity. So that's why it is a spin forbidden one. So this is spin forbidden relaxation. But this is very important one. It doesn't mean that the reaction will not take place via this state, though this is a spin forbidden process. Now, one of the reasons that the most of this photochemical reaction go via this triplet state, that this triplet state is highly populated one, and it is having the high in lifetime. So the lifetime of this triplet state, this is, I told you, this is 10 to the power minus 3 to 10 to the power minus 5 seconds. So much high lifetime in comparison to the singlet state, like it may have the lifetime of 10 to the power minus 9 seconds. So due to the higher lifetime and due to its highly populated state, the reaction usually go via the triplet state, although the reaction also photochemical reaction also takes place via the singlet state. So as I told you, the most of the photochemical reaction occur via triplet state because it is highly populated state, lifetime is very high. So but in few molecules, for example in olefins, the intersystem crossing is not efficient. Okay, so that's why it needs the energy. So and that's for that we need some donor molecule which can donate the energy. So like if you talk about the olefins, the intersystem crossing is very low. So that's why it needs energy transfer from some donor molecule. And this donor molecule is having very efficient lifetime, efficient intersystem crossing. So olefin, what I told you, this is not having efficient intersystem crossing, but donor molecule is having the efficient intersystem crossing. So donor molecule, for example, if we may have a carbonyl compound, may act as a donor molecule because it is having efficient intersystem crossing. Okay, so olefins, these are called as because it accepts the energy from the donor molecule. That's why we may call it a acceptor molecule, and donor molecule, which is the donor or its energy, it transfers its energy, or here it is also called as the quencher. So the process of this energy transfer from donor molecule to the acceptor molecule, this is called as the photosensitization. So process of energy transfer from donor to acceptor molecule. Acceptor molecule here, it is olefin, it may be olefin, whereas donor molecule, it may be carbonyl compound. Called as photosensitization. And this donor molecule is called as the photosensitizer. Is called photosensitizer, and acceptor molecule, whereas acceptor molecule which takes the energy from the donor molecule, it quenches the energy of donor molecule. So acceptor molecule is called as quencher. Okay, so one of the conditions for this energy transfer, so the donor molecule can only transfer the energy to the acceptor molecule when the energy difference between donor and acceptor is only up to this 5 kilocalorie per mole. So energy transfer occurs only when the energy difference between donor and acceptor is 5 kilocalorie per mole or 50 around 50 kilojoule per mole. Okay, so difference between the energy of a donor and acceptor, that should not be more than 5 kilocalorie per mole. Is not more than, difference between not more than 5 kilocalorie per mole. So this is the condition for the energy transfer. Now suppose if we have a donor molecule, this is our donor molecule or excited donor molecule, then it will interact with the some acceptor molecule, and after interaction it will transfer the energy to the acceptor molecule. So this acceptor molecule has become now excited during transfer, and this donor molecule will come to its ground state. So excited donor molecule interact with the acceptor molecule. During this interaction or during this collision, it will transfer its energy to the acceptor molecule, and now the acceptor molecule will get excited. It will come and it can undergo reaction. Donor molecule will again come back to its ground state, or otherwise we may represent it like this. Suppose if we have a donor molecule, and what I told you, the donor molecule, it should be a some carbonyl compound. Okay, so this donor molecule, after getting energy, light energy, it will go to the first excited state. This is in ground state. It will go to the first excited state. Via intersystem crossing, it will go into the triplet state. Okay, now this triplet donor, it will now transfers the energy to the acceptor molecule. This acceptor molecule is the olefin here, and after transferring, now this triplet, this acceptor is getting excited, and this donor molecule will come back to its ground state. This triplet acceptor molecule can now give the product. It can give the product. So in this way we can represent the energy transfer. Now suppose if we have a donor molecule, is suppose benzophenone is the donor molecule, one of the carbonyl compound, and suppose the acceptor molecule is suppose olefin. We should take olefin like butadiene. So in butadiene, the intersystem crossing is not very efficient. Means the reaction cannot go via the triplet state very easily. Okay, triplet state is not so much populated. That's why in butadiene reaction will not take place easily via the triplet state. So we need some energy transfer, and energy can be transferred by the carbonyl compound like the benzophenone, acetophenone, or some other carbonyl compounds. So suppose if we, by the diagram we may understand, suppose if we have a donor, one of the this donor molecule, and one is the acceptor molecule. Suppose this is our donor molecule, this is the ground state donor molecule, this is the excited state of donor molecule after getting energy, light energy. So it will go into the excited state, and now from this via intersystem crossing it will come into the triplet state. So this is our triplet state, and this is via intersystem crossing it may come to its state. So for benzophenone, if we take this donor molecule as a benzophenone, okay, for this the energy difference here, it is around 60 or 72 kilocalorie per mole, and this energy difference is around 69 kilocalorie per mole. So what you have seen, this due to small energy gap between this excited singlet and this triplet, the intersystem crossing in this benzophenone is very efficient. But we need the photochemical reaction in olefin compound, that is butadiene, and in butadiene the intersystem crossing is not efficient, energy cannot take place via the triplet state, so we need this donor molecule. Now suppose if we is having the acceptor molecule, suppose this is A and suppose this is our butadiene system, and for this butadiene this energy, this is very high one, suppose this is around 120 kilocalorie per mole, and it cannot generate this triplet state very easily, so we need one of this donor molecule. And in presence of this donor molecule, now after getting excited, if donor molecule after getting excited, it will interact with this acceptor molecule, and during interaction the energy transfer will take place during interaction like this. So as you can see, the energy transfer, collision and energy transfer will take place, and so this energy gap is around 60 kilocalorie per mole, and during this collision between excited donor and this acceptor, energy transfer takes place and reaction may takes place via the excited acceptor molecule. Now we may also represent this reaction, suppose if we have a benzophenone. So this benzophenone in ground state, after getting excited, after getting energy, it will go into the singlet state, then it will again via intersystem crossing, first of all after getting light energy, it will undergo excitation, it will go into the singlet state, via intersystem crossing it comes to its triplet state, and from this triplet state it will now interact with the donor, it will interact with the acceptor molecule. This is the acceptor molecule, that is butadiene. It will interact, and after interaction this acceptor will undergo excited. This will go to the excited state and it will loses its energy and come back to its ground state. Now this triplet butadiene being highly populated, it will give the reaction product. Now it may give the reaction product. So it gives rise to three products. One of the product that we can write, this is one of the product, and this is the another one. And this actually, this butadiene, it interacts with another molecule of butadiene. It dimerizes to give this product. So if I write, this is the first one, this is second, this is third, and this is fourth one. So these are the dimers actually. These are the dimers when a triplet butadiene interacts with another molecule of butadiene. And that butadiene, either it may be a singlet butadiene or it may be a triplet butadiene. So this would be obtained. So suppose in a brief what I can write, this butadiene, if we are irradiating it and then via triplet state in presence of sensitizer, this is giving this product, three products, and via singlet state in absence of sensitizer, we get two products. This is one of the product and this would be the another product. So these are monomer actually, we can say these are the dimers, and this butadiene it rearranges to give these two product. So here I have described the energy transfer in alkenes, okay, where is some carbonyl compounds transfer its energy to the alkene molecule. Now come to the intramolecular energy transfer. Where one part of molecule transfers the energy to the another part of molecule. One part of molecule transfers its energy to the other part of molecule. Okay, so if we take example, then suppose if we have a benzophenone, and to this benzophenone at this fourth position we have naphthyl alkyl group. Okay, so we can have a absorption band due to this benzophenone, and due to this naphthyl alkyl part we can have a independent absorption band due to this one and this one. Now suppose if we irradiate this molecule with a radiation which is absorbed by only benzophenone, okay, then in emission spectrum we will get the absorption band due to this naphthyl alkyl part also, and this occurs due to the energy transfer and this via the triplet energy transfer. Okay, so what I am telling you, if we irradiate this molecule with a wavelength, if we irradiate this complete molecule with a wavelength absorbed only by this benzophenone, then we can find the absorption band due to this naphthyl alkyl part in the spectrum. So this can only happen via the energy transfer process, via the triplet energy transfer process. So this is an example of intramolecular energy transfer. So actually we are only irradiating by this particular irradiation by the wavelength absorbed by this benzophenone. It will transfer this energy, it will transfer this energy to this part, and the UV visible spectrum will show the band due to this one. So this is one of the examples. In the same way, Suppose if we have a okay, so now suppose if we are irradiating this molecule, and after means here n to pi star transition will takes place when we are irradiating this, because and this n to pi star transition means this carbonyl part, because it is having the n electrons to carbonyl part, it will absorb the radiation, and when it absorbs the radiation, the product that we are getting, that is cis product, means isomerization reaction will take place here, and we will get the cis product that we are getting. Or we can say these two groups, now these are on the same side, these two on the same side. So this isomerization reaction is only possible via the intramolecular energy transfer. Now here the light is absorbed by this part of the molecule, and it will transfer its energy, and after transferring the energy, the isomerization reaction will take place in this alkene molecule. So this is the another example of intramolecular energy transfer. Now this energy transfer can also be shown by the molecular orbital concept diagram. So molecular orbital diagram for energy transfer process. Okay. Now, so in energy transfer process, what I have told you, this donor molecule, excited donor molecule interact with the acceptor molecule. It will transfer its energy to the acceptor molecule. Now acceptor molecule becomes excited, and donor molecule then comes to its ground state. So this can be shown by the molecular orbital concept also. Suppose we have this molecular orbital for this donor molecule. This is suppose donor molecule, and 2 electrons in the ground state donor molecule, and when both donor and acceptor molecule are in ground state, and this is our acceptor molecule. So now this will, after irradiation, here both donor and acceptor are in ground state. After irradiation, the donor molecule will become excited. As I have shown, the donor molecule, because it is having the higher energy, that's why I have shown at the higher one. And because what I have told you, the condition for energy transfer is that the donor molecule should always be, the energy of donor molecule should be higher than that of energy of acceptor molecule by 5 kilocalorie per mole. So donor molecule is shown to be present at higher energy, acceptor are at lower energy. After irradiation, okay, this donor molecule will become excited. One of the electron is going into here, excited state, and now we have this acceptor molecule. So this is excited donor, and we have here acceptor molecule. So this acceptor molecule now it can transfer its energy to the acceptor molecule. So after transferring it, how we can show it? We can show in this way. This is now donor and now acceptor. So this electron, this energy transfer, this is the energy transfer that I have shown over here. This is the energy transfer, and now the electron is coming to here. The electron is coming over here, and finally after transferring the energy, once the acceptor molecule has gained the energy, okay, so this is the excited donor. This is the excited donor. After transferring its energy to the acceptor molecule, now donor molecule will come into its ground state. So again, now this will transfers. Now this will come into its ground state, and we may show it again. Now it is coming into the ground state, and acceptor molecule is in excited state after getting the after getting excited. Now this is the acceptor molecule. It has gained the energy. Now it can react. After the gaining the energy, it can react, or it will go into the triplet state, and finally it will give you the product. So like this we can show the energy transfer process by the molecular orbital diagram. Thank you. Now in my next lecture I will explain during energy transfer process the formation of exciplex and eximer takes place. Okay, thank you.